The syntax of first-order logic is almost identical to that of Hebron logic. Every syntactically legal sentence in Hebron logic is a syntactically legal sentence in first-order logic. The only difference is that first-order logic has one additional type of sentence. An equation is an expression of the form sigma equals tau, where sigma and tau are terms in our language. An equation is a way of stating that two similar, the same, or possibly distinct terms refer to the same object. For example, to express the coreferentiality of plus 2, 2, and 4, we write plus 2, 2 equals 4. We can also distinguish terms by writing negated equations. To say that plus 2, 3, and 4 refer to different objects, we write not plus 2, 3 equals 4, which we sometimes abbreviate as plus 2, 3 is not equal to 4. In what follows, it's useful to treat equations as atomic sentences. In Hebron logic, the only atomic sentences are relational sentences. The notions are identical. In first-order logic, we have two types of atomic sentences, relational sentences and equations. Other than this one small change, the languages of Hebron logic and first-order logic are the same. The real difference between the two logics is a semantic one. In first-order logic, object constants refer to objects in some application area. Function constants refer to functions on these objects, and relation constants refer to relations. Such interpretations are used in defining the truth or falsity of first-order language sentences. This notion of interpretation is the source of much of the expressive power of first-order logic. Unfortunately, with this power comes somewhat greater complexity, as we shall see. The key notion, again, in first-order logic semantics is that of interpretation. An interpretation is a universe of discourse, let's call it U, together with a mapping from constants of the language into the elements of U, functions on U, and relations on U. Here's that same definition stated a little more precisely. The universe of discourse of an interpretation, I, written here as I enclosed in vertical bars, is an arbitrary set of objects. Again, let's call it U. Each object constant A in our language is mapped into an element of U. Each function constant F with arity N is mapped into an n-ary function on U. Each relation constant R with arity N is mapped into an n-ary relation on U. For example, here's an interpretation for a first-order logic language with object constants A, B, and C, with unary function constant F, and with unary function constant relation constant P, binary relation constant Q, and ternary relation constant R. Our universe of discourse in this case is a set consisting of the numbers 1, 2, and 3. Our interpretation maps A to 1, B to 2, and C to 2. It maps F to a function that gives one and only one value for each element in the universe of discourse. 1 is mapped to 2, 2 is mapped to 3, and 3 is mapped to 3. And the interpretation maps P, Q, and R to relations of the appropriate arity. Note that more than one object constant can refer to the same object. In this case, B and C refer to the number 2. Also, not every object in universe course need have a constant that refers to it. For example, there's no object constant that denotes the number 3. The function f assigns one and only one value to every number in the universe of discourse. By contrast, in the relations, some objects are paired with other objects, whereas some objects do not appear at all. A variable assignment is for variables what an interpretation is for object constants. Given a universe of discourse U, a variable assignment is an arbitrary mapping from the variables of the language into U. A value assignment based on an interpretation I and a variable assignment V is a mapping from all of the terms of the language into the universe of discourse. The mapping must agree with I on constants. It must agree with V on variables. And the value of a functional term is the result of applying the function corresponding to the function constant to the objects designated by the terms. Let's see an example. Given the interpretation of variable assignment shown here at the top, we have the following value assignments. The value assignment of the constant a is 1 because that's the value under the interpretation I. The value assignment of the variable z is 2 because that's the value under the variable assignment v. The value assignment of the term f of a is 2 because that is the value of the function f applied to the value assignment of a. Remember, a has value 1, and looking in the interpretation of f, we see that 1 has value 2. Hence, the value of f of a is 2. And finally, the value assignment of the term f of z is 1 because that's the value of the function applied to the value assignment of z. The truth assignment, based on interpretation I and variable assignment v, is the mapping from the sentences of the language to true or false. The details depend on the type of sentence involved. Given an interpretation I and a variable assignment v, a relational sentence is true if and only if the tuple of objects denoted by the arguments is contained in a relation denoted by the relation constant. For example, given the interpretation and variable assignments we saw earlier, we have the truth assignments shown here. The relational sentence R of AB is true because the tuple, consisting of 1 and 2, is a member of the relation assigned to the relation constant R. And the sentence R of ZA is false since 2, 1 is not in R. Given an interpretation I and a variable assignment v, an equation sigma equals tau is true if and only if the object denoted by sigma is the same as the object denoted by tau. If and only if the semantic value of sigma is identical to the semantic value of tau. For example, given the interpretation of variable assignment shown here, we can see that the object constant a and the term f of b have the same value assignment, and hence the equation f of a equals f of b is true. Conversely, a and f of x have different values, and hence the equation a equals f of x is false. The conditions for truth of logical sentences in first-order logic are analogous to those for the truth of logical sentences in propositional logic and Herbrand logic. A negation not phi is true if and only if phi is false. A conjunction phi and psi is true if and only if both phi and psi are true. A disjunction phi or psi is true if and only if phi is true or psi is true, or both. And an implication is true unless the antecedent is true and the consequent is false. And equivalence is true if and only if the truth value of the two embedded sentences are the same. Now on to quantified sentences. Intuitively, a universally quantified sentence is satisfied if and only if the embedded sentence is satisfied for all values of the quantified variable. And intuitively, an existentially quantified sentence is satisfied if and only if the embedded sentence is satisfied for some values of the quantified variable. Sadly, expressing this intuition, at least expressing it rigorously, is a little bit tricky. And in order to do so, we need the notion of a version of a variable assignment. Then we can give a rigorous definition to intuition by talking about some variations or all variations of a given variable assignment. A version, often written of a variable assignment v, often written v where omega is replaced by x, or v omega gets x, is the variable assignment that agrees with v on all variables except omega, which is assigned the value x in the version. So v of omega give x applied to an arbitrary variable theta is going to equal x if theta and omega are the same, and v omega gets x applied to theta is going to be v of theta if theta and omega are different. Okay, here's some examples. Let's take the variable assignment shown here in the upper right. All of the variable assignments at the bottom are versions of this variable assignment. In the first, we assign x to 1. In the second, we assigned x to 2. In the one in the lower left, we assign y to 1. And in the one in the lower right, we assigned y to 2. And these assignments, these versions, overwrite whatever was in v in the original variable assignment. Okay, now, with this notation, we can finally formalize the semantics of quantified sentences. An interpretation I and a variable assignment v satisfy a universally quantified sentence for all new phi, if and only if I and v satisfy phi for all versions of v that can be defined over the universe of discourse of I. And an interpretation I and a variable assignment v satisfy an existentially quantified sentence, there exists a new phi, if and only if I and v satisfy phi for at least one version of v that can be defined over the universe of I. Okay, here are some examples. Consider the sentence for all x R of xx. This is true under the interpretation of variable assignment shown if and only if the scope is true for all versions of the variable assignment. While it's true for the second version, it is not true for the first version, and so the sentence as a whole is false. By contrast, since the scope is true for at least one version of the variable assignment, the interpretation of variable assignments satisfies the existentially quantified sentence shown on the right. When quantifiers are nested, this computation becomes messier, but the definitions still work. Here you see a couple of examples. I'm not going to read through the examples. However, I recommend that you pause the video here and study these examples till you're comfortable with the answers. Now, if you think this is complicated, you're not alone. Students seeing the semantics of first-order logic for the first time are often bewildered. The intuition behind the semantics is simple enough, but the details are really complex. Much more so than for Hebron logic. To see this, compare the semantics of universally quantified sentence in the two logics. In first-order logic, we say that a universally quantified sentence is true in an interpretation and a variable assignment if and only if the scope is true for the interpretation and every version of the variable assignment compatible with the interpretation. It's quite a mouthful. In Hebron logic, we say that a universally quantified sentence is true in a truth assignment if and only if every instance of the scope is true. Hebron logic definition is simpler, and for many people it's more intuitive as well. We'll talk more about this in a later segment. Let's look at a few definitions and some observations before we close out this segment. An interpretation I and a variable assignment v are said to satisfy a sentence if and only if the sentence is true according to the rules we've just seen. An interpretation of a sentence is said to be a model if and only if it satisfies the sentence for every compatible variable assignment. So models are special cases of interpretations. Remember that an occurrence of a variable v is free if and only if it does not lie in the scope of any quantifier, and a closed sentence is a sentence with no free occurrences of variables, otherwise the sentence is said to be open. Now let's use these two concepts in a couple of observations. If an interpretation satisfies a closed sentence for one variable assignment, then it satisfies the sentence for every variable assignment. In other words, it's a model of that sentence. You should think about this to convince yourself that it's always true. And here's a second observation. An interpretation is a model of an open sentence if and only if it's a model of that sentence obtained by universally quantifying all of the free variables in the sentence. Again, think about this to convince yourself that it's true.